Hello guys, and welcome to another calculus video. In this video we're going to be solving a discrete functional equation, which is the one pictured right here, and we're going to be using an incredibly powerful tool known as the Z-transform. So first let's discuss what the Z-transform is. This is the notation we're using here. Z of f of n is equal to f of z, and this might remind you of the Laplace transform of f of t. This is equal to f of s, right? This is actually basically the exact same thing, only this time we're talking about discrete variables, or discretely defined functions rather than continuous functions. So it's essentially the same thing as the Laplace transform, and similarly it can be used to solve not only functional equations but difference equations, which are the discrete equivalent of differential equations. So difference equations usually look something like f of n plus 1 equals, I don't know, n f of n, something like that. And this is something that would be really useful when we're using the Z-transform. And it's essentially the equivalent of like y prime equals xy or something like that. And that would be the continuous equivalent. So let's discuss what the Z-transform is. So the Z-transform of a discretely defined function, this time we're going to be using the unidirectional definition of the Z-transform, which means that we're summing from n equals 0 to infinity f of n times z to the negative n. There is also a version which would be the bidirectional, which would be the sum from n equals negative infinity to infinity, but that doesn't really help us in our current journey. So we're not actually going to be using that definition. And this is also going to be equal to capital F of z, since we're going to get out a function of z. And you can kind of see that this is going to be equal to f of 0 plus f of 1 over z plus f of 2 over z squared, dot, 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 right? So if we want to take the inverse z transform of f of z, the way we're going to do this, there's not really good notation for this. We're going to expand f of z into what's called a Laurent series, which looks like this. It's essentially a power series in 1 over z, which is exactly what we're going to do. And that will actually tell us these coefficients, f0, f1, f2, will actually tell us our original function, f of n. And the reason we're using this odd z transform is because it has a lot of interesting properties that are going to help us greatly. So yeah, so we're going to, this Z-transform kind of uses a bridge between Taylor series and power series and their functional components, right? So they're going to be super helpful in lots of different cases, and all we have to know how to do is sum things up and expand other things into infinite sums. So let's go ahead and solve our problem. So we're going to pretty much treat this the same way we would a differential equation in terms of the Laplace transform. So we're going to be doing essentially the same thing. We're going to have f of n equals 2 to the n minus sum from k equals 0 to n of f of k. And before I go ahead and take the z-transform of this, I want you to think of the continuous version of this equation would be something like y equals 2 to the x minus the integral from 0 to x of y dx, right? So this would kind of be a similar situation. You could replace y with f of x, right? Only this time we're doing the discrete equivalent. So what are we going to do? We're going to take the z-transform of both sides. So on the left side, we're just going to have capital F of z, and this is what we're going to be solving for. And on the right side, 2 to the n is super easy. We just have to plug it into our definition, sum from n equals 0 to infinity of 2 to the n, z to the negative n. We can see that this is the same as the sum from n equals 0 to infinity of 2 over z to the n. And we're going to assume that it converges, so we're essentially choosing a value of z which is greater than or equal to 2, right? And so then we're going to end up with 1 over 1 minus 2 over z. And this is just going to become z over z minus 2. So we can write that right in here. Next, we're going to take the z-transform of sum from k equals 0 to n of f of k. And this is a bit of an interesting situation, so I'm going to go ahead and erase this so we can have some more space. And this is another really interesting property of the z-transform, and you might find some parallels to the Laplace transform as well in this situation. So if we're summing from n equals 0 to infinity, the sum from k equals 0 to n of f of k times z to the negative n. Now, the main thing that we're going to want to do here is exchange the order of summation and integration, of course, or exchange the order of summation. We don't have any integration here. So we're going to go ahead and flip these. And k is going to be summed from 0 to infinity, of course, because as you can see, as n goes to infinity, k is also going to go to infinity. And n is going to go from, if we sort of visualize this here with a little graph, we can say n and k, and then we're going to have all these different points, right? Every time we have a value of n in this original summation, we're going to have k take on all the values up to that. So that's going to look something like this, so on and so forth up to infinity. However, once we exchange the order of summation, we can see that every time we pick a value of k, say this value of k, we're going to pick values of n starting at k and going all the way out to infinity. So we're going to go from n equals k to infinity, right? And this is going to be the sum of f of k, z to the negative n, but we can actually just bring f of k all the way outside here, and we're going to have z to the negative n. And this is a super simple summation, since this is just 1 over z to the n. If we go ahead and evaluate this inner sum, we're going to have the sum from k equals 0 to infinity of f of k, and then we're going to have, of course, 1 over 1 minus z, 1 minus 1 over z, sorry. And then we just have to multiply by the first term, which in this case is just going to be 1 over z to the k, right? So we can go ahead and bring this outside. And so this is going to be equal to z over z minus 1 times the sum from k equals 0 to infinity of f of k, z to the negative k. And this part right here is nothing but f of z, right? So that's a pretty interesting property that we can abuse sort of here. And so this actually turns our sum of f of k, which is akin to an integral, into just something times f of z, which is super useful in this situation in a sort of equation that might be more difficult to solve if we weren't able to just reduce this to an algebraic expression. So we're just going to be subtracting z over z minus 1 times f of z. And then if we could just go ahead and solve for f of z, we're going to get f of z. We're going to have z minus 1 plus z all over z minus 1, just combining those fractions, equals z over z minus 2. And if we solve for f of z, we're just going to get that f of z equals z times z minus 1 over z minus 1, or sorry, z minus 2 actually, z minus 2 to z minus 1. And a cool trick that I actually want to mention here is, in general, when you're taking the z-transform, you want to solve for f of z over z, because that's going to make things easier later. So we're just going to go ahead and do partial fractions on this. Now I've already done it before, and you guys know how to do partial fractions, so I'm just going to go ahead and put the answer right here. So the answer is just going to be f of z over z equals 1/3 over z minus 2 plus 1/3 over 2z minus 1. And then we can go ahead and just multiply by z on both sides. And again, the z-transform has lots of different tricks that you can apply to it. And similar to the Laplace transform, if you know the z-transform of common functions, you can pretty easily come up with a set of simple rules and be able to take the z-transform of almost any, or take the inverse and the forward and the inverse z-transform of almost any function. But I'm just going to go ahead and do the derivation for those in each case here. So again, what we want to do is find the Lorentz expansion of f of z, or expand it as a power series of 1 over z. So let's see how we're going to do that. So the first thing we're going to do is we're going to put everything in terms of 1 over z. So we're going to divide by z on the top and bottom here, and we're going to end up getting 2 minus 1 over z here, and 1 minus 2 over z. And this 1/3 on the top. And then in this one on the right here, I'm going to actually also divide by 2. So we're going to have 1/6, 1 over. So you can see we have pretty similar things here on both sides. But the important part is that we have 1 over 1 minus x. And this is just a geometric series and can be expanded to the sum from n equals 0 to infinity of x to the n. And this is actually exactly what we want here. So if we write f of z right here, we can see that this is going to be 1/3 the sum from n equals 0 to infinity of 2 over z to the n power, plus 1/6 the sum from n equals 0 to infinity of 1 over 2z to the n power. And this is exactly what we needed in order to evaluate our original expression. We needed to expand it as some powers of z to the negative n. So if I just go ahead and reorganize the sum instead to 1, we're going to get that f of z equals the sum from n equals 0 to infinity of 1/3 times 2 to the n plus 1/6 times 1/2 to the n, all times z to the negative n. And since this is our z-transformed version, that means that this is our original discrete function. So that means that f of n is just equal to 1/3, 2 to the n, plus 1/6, 1/2 to the n. So overall, I think this was a pretty interesting problem. I know that the Z-transform is not very well known outside of signal processing and differential equations and those sorts of things. So I hope you guys learned a lot about the Z-transform in this video, because I think it's a really, really powerful tool, not only for evaluating infinite sums, but very often when solving a differential equation, if I want to find a power series solution, the easiest way to solve that is going to be applying the Z-transform to a difference equation. So the Z-transform is definitely a handy tool to have, and if you're ever solving any kind of discrete equation or difference equation, it's the perfect tool for that occasion. So I hope you guys learned about a lot about the Z-transform, and I hope you guys enjoyed the problem. And yeah, see you next time. Hope you enjoyed the video. Bye.